What if I told you there are insects living in your flour right now?
Before you throw out your pantry, this discovery in Australia might actually save millions of lives.
It's 2019, a warehouse in Sydney, Australia. Workers are checking bags of flour. Standard routine. But today, something's different. They find tiny holes and movement. Insects.
This happens more than you'd think. Every year, stored grain pests destroy 20% of the world's grain supply.
That's enough food to feed 400 million people. Just gone.
The main culprits? Flour beetles and weevils, tiny bugs with a massive appetite. Here's how it works. A female beetle lays eggs inside grain kernels.
The larvae hatch, they eat, they grow, they multiply.
One beetle becomes hundreds in just weeks. And here's the worst part. By the time you see them, it's already an infestation.
For decades, we fought these pests the same way. Chemical pesticides.
Spray the grain, fumigate the warehouses, hope for the best.
But there's a problem. These bugs are getting smarter. They're becoming resistant. Plus, consumers are worried. Nobody wants pesticides in their food. Organic markets are booming. Regulations are getting stricter. The old methods aren't just failing, they're becoming unacceptable. So scientists needed a new approach, something natural, something sustainable.
Enter Dr. Philip Taylor, an entomologist at Australia's National Science Agency.
He's been studying these pests for 20 years. He knows everything about them. What they eat, how they breed, how they think. And he has a wild idea. What if instead of killing the insects with chemicals, we use their own biology against them? It sounds like science fiction, but Taylor thinks it's possible. What's happening inside these bugs at a molecular level? So his team starts collecting beetles, thousands of them, from warehouses across Australia. They bring them back to the lab, and they start asking questions. How do these insects digest grain? What genes control their reproduction?
What makes them tick? The answers they find will change everything.
The team sequences the beetle's DNA. They map their entire genome. It's painstaking work, month after month in the lab. Testing, analyzing, looking for weaknesses, and then they find something interesting. A specific gene that controls the beetle's ability to digest starch. Without this gene, the beetles can't break down flour. They can eat all they want, but they'll starve. It's like being lactose intolerant, but deadly. This is the vulnerability Taylor was looking for.
But here's the challenge. How do you turn off a gene in wild insects? The answer comes from a technique called RNA interference. You create a genetic instruction that tells specific genes to shut down.
It's like sending a turn-off signal directly to the beetle's DNA. The beauty? It only affects the target pest. But there's a massive problem. How do you deliver this genetic instruction to beetles living in tons of stored grain? You can't inject each one individually. You need millions to eat it voluntarily. Taylor's solution? Hide it in bait. Make something so irresistible that beetles can't help themselves.
His team spends 2 years testing formulas. They try different grains, different attractants.
Different delivery methods. Most fail. The beetles ignore the bait. Or the RNA breaks down too quickly. It's frustrating.
They're so close, but something's missing.
Then, a junior researcher named Emma has an idea. What if they're overthinking this? Beetles are attracted to damaged grain. It signals easy food. What if they just made the bait smell like damaged flour? They try it, and the beetles go crazy for it.
Now they have the delivery method, but they need to test it. They set up a trial in a small grain storage facility. They release beetles, wait for them to establish, then introduce the bait.
Day 1, nothing. Day 2, nothing. Day 3, the beetles find it, and they feast. Within a week, the beetles stop reproducing.
Within 2 weeks, the population crashes.
Within a month, they're gone. No chemicals, no fumigation. Just the beetles' own biology turning against them. It works. It actually works.
It works. It actually works. But here's where it gets complicated. They need approval to use this commercially. That means years of safety testing.
Environmental impact studies, regulatory reviews. And not everyone is convinced. Some groups worry about genetic technology in food systems. Others question long-term effects.
Taylor's team addresses every concern. They prove the RNA breaks down rapidly.
It doesn't persist in the environment. It doesn't affect beneficial insects. It leaves no residue in flour. Study after study shows the same thing. It's safe, it's effective, it's revolutionary.
In 2023, Australia becomes the first country to approve RNA-based pest control for stored grain. It's a historic moment. After 4 years of development, they're ready to scale up.
But will it work in the real world? The first commercial deployment happens in Queensland.
A massive grain storage facility with a serious beetle problem. They've tried everything.
Pesticides barely make a dent anymore. Taylor's team arrives with their bait.
The warehouse managers are skeptical, but desperate.
They place the bait strategically, monitor the beetle population, and wait. The first week, beetle numbers actually increase slightly. People start to panic. Is it working at all? Taylor tells them to be patient. The effects take time. Week 2, the beetle population stabilizes. Week 3, it starts dropping. Week 4, it's down 70%. Week 6, they can barely find any beetles.
The warehouse staff can't believe it. In their entire careers, they've never seen results like this.
Word spreads fast. Other facilities want in.
Within 6 months, the technology is being used across Australia.
The results are consistent. Beetle populations crash. Grain losses plummet. Chemical use drops to nearly zero. But the impact goes beyond just pest control. Workers are healthier. No more exposure to harsh pesticides. The grain is cleaner. Consumers are happier. And the environment benefits too. No toxic runoff, no harm to pollinators. It's a win across the board. But Taylor isn't satisfied yet. His team is already working on the next generation, targeting other pests, weevils, moths, mites. Each one requires custom RNA sequences. But the framework is proven. Other countries are watching closely. Canada, the United States, India, everyone wants this technology. By 2024, trials are starting worldwide. Early results mirror Australia's success. In India alone, this could save enough grain to feed 50 million people annually. That's the true impact here. This isn't just about killing bugs. It's about food security. Think about it. 20% of stored grain was being destroyed. That's 1/5 of the food we carefully grew, harvested, and stored, just wasted, eaten by pests we couldn't control. Now we can protect it without harming people or the planet. That's transformative. And it started with a simple question. Instead of asking, how do we kill these pests, Taylor asked, how do these pests work? He looked deeper. He found the mechanism. He used nature against itself. That's the power of understanding your enemy. So those insects in Australian flour, they weren't just a problem. They were a teacher. They showed us that the best solutions often come from understanding biology, not fighting it. This approach is now being applied to other agricultural pests, locusts, aphids, crop destroyers worldwide. The lesson here goes beyond pest control. When we face problems, especially big ones, we often reach for the hammer, the quick fix, the chemical solution. But sometimes the answer is already there, in nature, in the system itself. We just need to look closer. Next time you open a bag of flour, remember this story. Remember that scientists turned a plague into a breakthrough. And that breakthrough might help feed the world.
If you found this interesting, share it with someone who loves science, or food security, or just really hates bugs in their pantry. Thanks for watching.